What makes the color of one's skin change? Skin color is determined mainly by melanin pigment in the epidermis and hemoglobin pigment in the dermis. Changes in these two pigment components cause skin color to change. Image-based skin color and texture analysis synthesis technology is the product of the fusion of the latest dermatological research and information and image sciences. With this technology, it is now possible to isolate and extract the pigment component distribution data, which make up skin color, and use that data to synthesize skin colors. Here we will explain the process of analyzing skin pigment components. By using polarized light, it is possible to capture a reflected image of the skin's inner layers void of reflected images of the skin's surface. Using this reflected image of the skin's inner layers, the skin's pigments are separated into melanin and hemoglobin components. Extracting pixels from an image of a flat portion of the skin and creating an RGB plot in logarithmic space results in a nearly two-dimensional planimetric distribution. Applying independent component analysis, it is possible to determine the melanin and hemoglobin component vectors which are on the two-dimensional plane. However, when this technique is applied to the entire face, with its uneven surface, shading becomes a factor, and the distribution of the skin's pigment components expands into a three-dimensional configuration. Shading data, therefore, becomes mixed together with pigment component distribution data. The image-based skin color and texture analysis synthesis technology we propose compresses the expansion of the distribution along the shading dimension. We can thus generate distribution data of skin pigment components without shading data. We used this technology to analyze a rectangular area of skin 2 weeks after we artificially caused it to tan. And our results showed that the rectangular pattern appeared only on the melanin pigment component image, matching the tanned portion of skin. We also stimulated blood flow in a certain portion of skin by applying methyl nicotinate to it and analyzed the result. Our results showed that the pattern in which we applied the methyl nicotinate appeared only on the hemoglobin pigment component image. Our technology thus makes it possible to remove shading data and extract only precise distribution data of skin pigment components. Reversing the process of skin image analysis, we were able to develop our synthesis process. Using this technology, the various changes in pigment that occur in response to changes in the body can be simulated. Working with a photo image, how it would appear with a lower amount of only melanin pigment. Here we compare the synthesized image of a tanned face with an image of the face prior to tanning. As people age, the texture of melanin pigment components changes. To demonstrate this change, we analyze the melanin pigment component image of a woman in her 50s and synthesize this image by gradually converting her melanin texture pattern to that of a woman in her 20s, using a pyramid-based texture analysis synthesis technique. We also applied this technique to the entire face. Overall, the face now has a rejuvenated youthful appearance. An appearance that approximates that of this woman's daughter, who is in her 20s. As we have just demonstrated, we have made it possible to use image-based skin color and texture analysis synthesis technology to perform simulations of skin color and texture or distribution based on the skin's physiology, and show the results of changes in pigment amounts and distribution of pigment components.